Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is a lecture on Bayesian Linear Regression. It's part of the course Analytic Methods for Lawyers. It's intended, though, not only for lawyers and law students, but also for anyone interested in technical topics and the Wolfram language. Before we get to Bayesian regression, though, I think it's time for a second look at just standard linear regression. When we do linear regression, we usually get some best fit. We fit a line to points or a plane to points. But really, that's not the entire picture. And if we use maximum likelihood estimation, what we're really deriving is a multivariate probability distribution over the regression coefficients. I'm going to call that distribution big script T. And that distribution, like any multivariate distribution, has marginal distributions. In this case, there would be n of them, where n is the number of basis functions, including the constant term, that you used for the regression. So that when you see things like p-values attached to a regression coefficient, here this p-value is attached to this regression coefficient, this p-value is attached to this regression coefficient, what in fact you're seeing is a rarer probability, and it's a rarer probability of the marginal distribution associated with that regression coefficient distribution translated to lie centered at 0, 0, and then evaluated at this particular number. Okay? Or when you see this number, this 0.0018, what you're really seeing is the second marginal distribution of that multivariate regression coefficient distribution script T, translated to be centered at 0, 0, and then evaluated at, in this instance, 1.9. And similarly, when you see a confidence interval for a regression coefficient, what you're really seeing, again, is let's go back to that multivariate distribution. Let's take the marginals, and then let's get the 0.025 and 0.975 quantiles of those marginals, and that's going to give you the confidence interval, at least if you want a 95% confidence interval. And so this is sort of operating behind the scenes in many regression packages, but one of the really nice things about the Wolfram language is it lets you obtain this distribution, script T, so you can kind of better understand what's going on. The other thing is that if you understand where big script T, that multivariate regression distribution, comes from, you're going to be well on your way to understanding the otherwise somewhat inscrutable topic of Bayesian regression. And why are you almost there? It's because really what Bayesian regression does is it just modifies the multivariate probability distribution based on a prior distribution for the regression coefficients. Okay, that may have been hopelessly abstract. Let's take a concrete example and work it through. Let's start with 5x values, 1, 2, 3, 5, 9. And we're going to have y values that happen to be 2x plus 3 plus noise. And I'm going to compute the noise in a special way. I didn't have to do it this way, but I think it does help illustrate some of the features of Bayesian regression. Imagine that each x value comes with a particular z-score, and that z-score is drawn from the normal distribution, so that the actual noise associated with any point is that z-score multiplied by some constant value, which I'll call spread. So if spread is some high number, then the noise is generally going to be high, unless you have a tiny z-score. And if spread is small, well, then the noise is going to be small, unless, of course, you have a very high z-score. So let's come up with some z-scores here for each of the 5 points. And what I should do, which is I should do this at the start of every video, is let's get our kernel cleaned up, because usually I'm doing this after I've done some other work. All right, we should have a clean kernel. And again, let's add to the drama by, there we go. Let's add to the drama by deleting the outputs. So we'll delete all of the outputs. Okay, great. Okay, so let's get those z-scores. And now let's write a function RV that takes a spread value, and then it computes for each of these 5 x values a y value. How do we do that? Well, we've got a map thread, and the first element of each list is just the x value, and the second element is 2x plus 3 plus the spread times the associated z-score. So there's our function, and if we evaluate RV with a spread equal to 1, here's what we get. And of course, in the real world, you never see what's going on behind the scenes. If you could see what was going on behind the scenes, there'd be no need to develop a model. You'd just know. But in the real world, you have to figure out what the model most likely is, or what the distribution of models are based on the data. Anyway, here's our data. We can, of course, list plot it. And that's what it looks like, and maybe there's some line you could fit through there. But supposing the spread is 5. Now here's the data, and it's not so clear to me just from eyeballing it where a line should fall. I thought it might be interesting to see what the data looks like as I shrink the spread from 5 down to 0.1 in increments of negative 0.1. So let's build that little animation, and you can see that the points are sort of converging onto the true line as the noise shrinks to 0. Okay? So that's the concept of our data and its relationship to this notion of spread. Okay, let's keep going with a little more review. Let's recall our maximum likelihood estimation work with regression. And the idea is we have symbolic parameters b0 and b1, where b0 is the intercept term of a line and b1 is its slope. And what we're trying to do is to calculate the log of the PDF of some normal distribution whose mean is a linear function of the x value, and we evaluate that at the y value. And then what we do is, after we've computed those log PDFs, we're going to take the negative sum, thus the negative log likelihood. So let's do that. And we get a complicated expression, but really it just has b0s and b1s, and so we can ask Mr. Wolfram if he wouldn't mind minimizing the negative log likelihood for the parameters b0 and b1. And when we do that, we get a value for b0, the intercept term, at 3.31, and a value of the slope of about 1.93. So something like that. In any event, we can look at the a plot of what our negative log likelihood looks like for different combinations of b0 and b1. And actually, this isn't a contour plot. I think originally I was going to make it one, but we'll just call it a plot 3D, and I'll just put that in a different format. All right, so this is the negative log likelihood evaluated for different values of b0 and b1, and what you can see is that it's kind of a nice smooth valley with its nadir at about 3.3 and its b1 value of about 2 or 1.93, and you can also see that there are these ellipses that represent levels of equal negative log likelihood. So that's what we've got. When we do a computation of negative log likelihood, we can calculate where the value is minimized. That's what we do in maximum likelihood estimation. But we can also calculate the value of negative likelihood for things that aren't optimal. Okay, but now, instead of doing maximum likelihood estimation by hand, which is sort of what I did, let's do regression the typical way in Wolfram Language using linear model fit, which we have studied elsewhere in the course. So here's our data. Here's our basis function. It's assumed that there's another basis function 1. I could have added in, but I'm not going to do so because it's assumed to be there. And then our independent variable is simply x. So if we do that, we get this model, and we can use this model and extract things like the parameter table. And I showed this in the introduction to this video. You get an estimate for the best fit, and then you get a p-value along with some other things. And you get that for both of the basis functions. And by the way, you should notice that these numbers correspond exactly to the numbers I got when I did maximum likelihood estimation, which that's what's supposed to happen. We could also get a parameter confidence interval table, and this is going to tell us that we can be 95% certain that the true value of the intercept is between 0.43 and 6.19, and the true slope is somewhere between 1.34 and 2.52. Okay, so we have these numbers, but where do they come from, or at least where does the p-value really come from? Where does the confidence interval really come from? And so what I now want to do is to see if we can recreate that result so that we have a better understanding of that these numbers aren't coming out of the air. And to do that, I want to create a multivariate regression coefficient distribution, and we'll call it big script T. Okay? So how are we going to do that? Well, we're going to compute a couple of things. First of all, we're going to get the center of this regression coefficient distribution, and that is the value of the first coefficient and the value of the second coefficient. The second thing we want to do is to know how do the coefficients relate to each other. Maybe they're not independent. Maybe if this coefficient, if the intercept term is high, then probably the slope shouldn't be as high, otherwise it won't fit very well. And if the slope is very high, maybe the intercept term should be kind of low, otherwise the points also won't fit very well. So to learn how the parameters relate to each other, we're going to use a property we haven't seen before called the covariance matrix, and I'll assign that per tradition to the symbol sigma. By the way, that's a mu, so one thing you learn in this course is your Greek letters. And then the only other thing we have to do is you have to take something on faith. That is that T should be a multivariate T distribution, and it should be a multivariate T distribution with 3 parameters, a mean, a covariance, and something called degrees of freedom. And you're going to have to trust me that the degrees of freedom are the number of data points minus the number of parameters. So let's build that script T, the multivariate regression distribution, and we'll do that by creating a multivariate T distribution and making those arguments mu, sigma, and I think that's a nu actually, not a v. But before I do that, I better remember to tell the kernel about nu. All right, now the kernel knows from nu. Let's evaluate our script capital T. And now that I've fixed a little problem, let's plot the PDF of our multivariate regression coefficient distribution. And there it is. Okay, and you can see that there is some correlation between the B0 values and B1. We can look at this plot from above, and what we see again are ellipses. Funny how that is. Why, those ellipses look an awful lot like those ellipses there. So now let's do the following. It's a multivariate distribution. We can take marginal distributions. So let's take the first marginal and call it a script T1. And you'll see it happens to be a student T distribution. And we can see what it looks like. There it is. There's our distribution of B0. That's the distribution of B0. Here's the second marginal. also a student t-distribution, and this is the distribution of B1. And so now that we've got these marginals, let's take the 0.025 and 0.975 quantiles of them, 0.432 and 0.619. Now, where have I heard those numbers before? And I think I saw them right here, 0.432, 6.19. And so that's where the confidence interval is coming from. It is basically quantiles of the marginal distribution of the multivariate regression coefficient distribution. And if you think maybe that was just luck, let's do it for our second parameter, B2, 1.34 and 2.52. And if again we scroll up, we see 1.34 and 2.52. So I don't think I'm that lucky. All right, so now you know where confidence intervals come from when you're doing conventional regression. And if you followed what I just did, which is basically the construction of a regression coefficient distribution, then you are a long way to understanding Bayesian regression. Okay, as I said, we're basically close to Bayesian regression. Now, instead of computing the likelihood of each B0, B1 pair of coefficients as above, I'm going to weight each likelihood according to our prior understanding of the probability. And then we're just going to normalize the weighted probabilities. It's really the same thing we did when we looked at Bayesian statistics elsewhere in the course. Let me start with a toy example, and if you understand the toy, I really think you're going to get it. Okay, supposing that B0 and B1 couldn't just take on any values they wanted. There were only two possible values. Candidate 1, where B0 was 3.2 and B1 was 1.9, and candidate 2, where B0 was 3 and B1 was 2. Okay, so here's our list of candidates. And then we could do what I've done now a bunch of times before and compute the likelihoods for each of these candidates. So this is our function, and you can see, again, we're mapping the PDF, I'm not going to do the logs here, of a normal distribution with the mean of B0 plus B1 times the x value, and I'm going to evaluate it at the y value. Okay, so let's do it. And it's not going to be happy, okay, because I forgot to tell it what the candidates were. And now it should do it. Yeah, there we go. Okay, so we get these numbers, and I could, divide each of these numbers by their sum, but I'm going to have the computer do it for me. And I'm going to say, let's make a categorical distribution. The two categories are candidate 1 and candidate 2, and the probabilities are those likelihoods divided by the sum of the likelihoods. So if I do that, I get a categorical distribution, and you can see the probabilities right there. Okay, so I can also use the information function to get the probabilities out. And by the way, when you saw it here, the reason it's a little different is this is rounding. The probability of the first candidate is 0.203, and the probability of the second candidate is 0.797. But so far I haven't done Bayesian because I haven't used a prior. And now enter Reverend Thomas Bayes, and he says, look, supposing before you had your data, you thought the probability of the first candidate being the correct fit is 70%, and the probability of the second candidate being the correct fit was 0.3. What could we then do? Well, we could take those same likelihoods that we computed right up here and multiply each of them, multiply the first one by 0.7 and the second one by 0.3, and maybe I need a tiny digression here on multiplication in Wolfram language. If I do 3, 5 times 7, 8, what's going to happen is, this is not a dot product. This is element-wise multiplication. So it's going to do 3 times 7 is 21 and 5 times 8 is 40. So that's the little notation I'm using here. So that'll give us our posterior likelihoods, the likelihoods from the data multiplied by the prior likelihoods. And then it's just the same thing. I'm going to form a categorical distribution, candidate 1, candidate 2. I'll take those posterior likelihoods and I'll normalize it so that everything sums to 1, dividing it by the total. So there we go. I'll use information to get the probabilities out. And now, with our priors, the probability for candidate 1's gone up to 0.37, and the probability for candidate 2's gone down to 0.628. So we've definitely moved from our priors. The evidence has moved us from our priors, but not sort of as far as if we didn't have any priors to begin with. Okay. Now, supposing I had an uninformative prior. Supposing my prior was, I don't know which it is. I'm going to assume candidate 1 and candidate 2 are equally likely. So let's look at what happens now. And now, candidate 1 is 20.202. Candidate 2 is 0.797. That's exactly the same thing I got when I didn't use Bayesian regression. So in some sense, what Bayesian regression is doing is it's skewing the results from the data by using the prior. And what that tells us is, when you want to emphasize the evidence and not a preconception, you need to use an uninformative prior. Your prior distribution should have as high entropy as possible. But if you have a well-reasoned prior, if you really do think, hey, there's a good reason to think that it's 70% candidate 1, 30% candidate 2, then you can and should use it. Well, our fun with the toy problems come to an end, because in the real world we don't really have just 2 candidates for the pair B0, B1. We have an infinite number of candidates. And so that tells us a few things. First, our prior has to be some sort of continuous probability distribution. We can't just do what I did in the toy problem and calculate the likelihoods for the 2 candidates. We have to come up with some symbolic calculation that gets it for every possible candidate. And because I have an infinite number of possibilities, I can't really do a sum at the end. I have to do an integral. And while, Wolfram is really great at doing integrals, where you have dozens of coefficients to be estimated, imagine a regression with lots of terms in it, lots of basis functions, that integral can be hard. And so this is why basically people didn't do Bayesian regression until computation became swifter and there were clever algorithms, of which probably the cleverest is MCMC, for kind of emulating integration. But now that we have this, really you can do Bayesian regression, and in my opinion you should be doing Bayesian regression if you have any prior beliefs, and you should consider the regression as sort of updating your priors. So Wolfram Language has a terrific resource function called Bayesian Linear Regression, created by a guy named Stuart Smith, and it does the hard work for us. And it's very well designed. Syntax looks really exactly like linear model fit. Here's our resource function, here's our data, here's our basis function, and I'm doing a shortcut. Probably I should do that to indicate that there could be more than one, and our independent variable is x. So I'm going to run Bayesian linear regression on the data, and then it is going to produce a long output, a big association of stuff. It's not going to hide behind an object, and so I'll just map short over each of the values of that association. But you'll see this doesn't take any time at all. Done. All right. So we've got this association. Let's look at the keys of the association. And there they are. We've got 1, 2, 3, 4, 5, 6, 7 keys, some of which we're going to study right now. All right, 2 of them are super easy. Basis and independent variables. Okay? Basis is, it's 1 in x, the constant term in x, and the independent variable is x. Done. All right, the log evidence key. What's that about? Well, I think the best way to understand the log evidence key is it's kind of a measure of how successful your model was in explaining the data. I am going to compute the log evidence for different spread values. That's what that little pound sign is doing there. And I'm going to let the spread go from 2 to the negative third up to 2 to the fourth. And then I'm going to plot the spread value versus the log evidence. So here we go. Let's do a bunch of Bayesian regressions. And we're done. So here's what we can see. We can see that as the spread increases, the log evidence decreases. It's negative always in this example, but the log evidence is minimized when the spread is very small. And when the spread is very small, remember from up here, you basically have a line, and so if you can fit a line to it, it's going to be a very good fit. Whereas if the spread is big, your line isn't going to fit very well. All right, back down we go. Where did we get to? We are here. Okay, and so in fact, I can kind of show you this. I'm going to show you a plot in which you're going to see the points and kind of converging to the line as the shrinkage goes from 5 to 0.1 in increments of negative 0.1, and the plot will be labeled with the log evidence. So here it is. You can see the points converging towards the line as the spread decreases, and you can see the log evidence increasing up to whatever that was, negative 10 or something, starting at negative 26. So log evidence is basically a measure of how successful your model has been in fitting the data. Okay, let's go to the harder keys, which are the prior and the posterior. First of all, let's just get what the prior is. There it is, and you can see it's an association again, and we can get the keys out. And we can see that we've got 1, 2, 3, 4 things: the regression coefficient distribution, the error distribution, which I'm not going to say much about, the predictive distribution, and the underlying value distribution. Let's start with what I think is probably the most important thing, which is that regression coefficient distribution. That's what you're assuming at the start the distribution of the coefficients are. And it's a multivariate t distribution. You don't have to start with a multivariate t distribution, but for reasons that I think are above the scope of this course, it's a good place to start. So what you can see is that the first argument here is 0, 0. It's basically saying if I don't know anything, I'm going to assume that the intercept is 0 and the slope is 0. You're going to see this is saying that there's high variance, but nothing's correlated with each other. That's why these non-diagonal terms are 0, and we've got 1/100th of a degree of freedom. We don't have much data. And so we can see, I can tell you that, but let's just look at a picture of the PDF of this, and you can see that the prior, it does have a peak, and it's a little hard to interpret this, but I think the best way to see just how uninformative this prior is let's take the second marginal, okay? Marginal distribution going this way. And let's evaluate the survival function at 1, 2, 3, 4, and 5. If this is an informative prior, you're going to see that as our B1 value increases, you should see a decline in the survival function. Basically, our model will be killing off high values. Let's see if that's the case. And no, it isn't really. It's barely killing it off at all. So that the probability isn't getting any smaller, the likelihood isn't getting any smaller as we move away from the center. And that's exactly what we want. This is a very uninformative prior. We're going in this instance to let the data speak for itself. Similarly, let's look at the predictive distribution. The predictive distribution says, if I give you an x value, here's the distribution of y values I expect to see. So the way we're going to do this is we're going to say, get out the predictive distribution. I'm just, for the heck of it, going to say let x be 3, and let's look at the distribution of the PDF of y as y goes from negative 10 to 10. So there it is. It is most likely that the value is 0, but supposing I were to say again, what's the probability that the value could be as great as 10? Okay, so this, I'm using a little bit of a complicated function here, but the concept is, what's the probability that the absolute value of the y value is greater than 10, given that x is 3, with our prior predictive distribution? And after a moment's time, it's going to tell you, look, there's a 95% chance that you could be as far away as 10. And so we don't really have very much information about y, which again is exactly what we want. We want an uninformative prior in this instance. Otherwise, we could bias the results and the data wouldn't be speaking for itself. All right, well, what about not what the y value is, but where does the best fit line fall? What's the distribution of places the best fit line could fall if, I'm going to again set x equal to 3. This distribution of where the best fit line falls is called the underlying value distribution. Not my favorite name, but it's a great function, so I won't complain too much. And we can look at a plot of this, and we can see there it is, and I can actually overlay the predictive distribution and the underlying value distribution. And you can see that for the prior, these two fall on top of each other. What we'll see later is once we have data, these two are going to diverge. Time to look at the posterior. So we're going to bust out the posterior information that Bayesian linear regression has created. And what you'll see is, if you ignore all the details, it's got the same 4 keys as our prior did. And moreover, if you compare the posterior to the prior, dare I do that? I'm not sure it's going to fit, but we'll give it a shot. Oopsie, BLR1. What you can see is that the family of distributions remains the same. That is, for the regression coefficient distribution, it was a multivariate t before and it's a multivariate t after. The error distribution was an inverse gamma before, it's an inverse gamma after. The predictive was a student t before, it's a student t after. And the underlying value was a student t before and it's a student t after. All that's changed are the parameters of those distributions. It's those parameters that have been updated. It's very nice to have the updating process not change the distribution family. When this, and this is one of the reasons that this is the default type of priors that's used, when you are drawing from the same distribution family in the posterior as you are from the prior is called a conjugate prior. So if you hear that term, that's what we mean. All right, let's look at the PDF of the new regression coefficient distribution. This is the distribution we believe exists after we've been updated by data. And there it is in this beautiful oceany color. And let's compare the posterior distribution in ocean to the reddish prior. Okay, and what we can see is there's this peak sticking out. This is sort of what we've learned from the data. And although the peak doesn't look like it's not like towering over the red surface here, the only reason it doesn't seem to be towering is because this is all scaled logarithmically, because if I didn't scale it logarithmically, it would be even worse. Let's look at something. Let's look at the prior probability or likelihood that the coefficients were B0, B1 were 0, -5. And let's compare that to what it is after, what we think the likelihood is afterwards. So I'm going to take this PDF and divide it by that PDF. And what you're going to see is it used to be 3.7 million times greater. So that by using the data, we now have a much better sense as to whether this is plausible, and it is not plausible. Similarly, let's look at this 3.2 candidate. And I'm going to divide the posterior probability by the prior, the posterior likelihood by the prior likelihood, and we get 20,000 something. So that the data has increased the relative likelihood that the correct answer is 3,2 by a factor of 20,000. So the data is very powerful, and our posterior distribution is in fact quite different from our prior distribution. Moreover, now that we have a probability distribution, we can ask and answer interesting questions like, what's the probability, in light of the evidence, that the value of the second regression coefficient is greater than 5? Okay? Maybe if it were 5 or greater, that would be of some practical importance. So to do this, we're going to form the second marginal, and we're going to take the survival function and evaluate it at 5. All right? And we learn that it's actually very, very small, very, very unlikely based on this data that it's 5. That is not really the kind of information you can get out if you do conventional regression. You need to be doing Bayesian regression to get something like this. Moreover, we can now create something called a credible interval. Okay, this is the range of values for a parameter for which the cumulative probability that the correct answer falls within that interval is equal to some number, usually 0.95, although there's Professor McElreath, who writes wonderful books on Bayesian statistics, thinks you should use 0.89. You can email him to see why. But credible intervals are to Bayesian statistics as confidence intervals are to frequentist statistics. And I wish they didn't have the same initials, but they do. So let's actually compute a credible interval for our regression coefficient, B1, that slope term. And the way I'm going to do that is I'm going to take the marginal for the second variable, which is the B1 thing, and I'm going to compute the quantile of that distribution, the 2.5% quantile and the 97.5% quantile. And I get these values 1.56 and 2.31. What does that mean? That means, based on the data and our prior, we can be 95% certain that the correct slope is between 1.56 and 2.31. Now, here my quantiles were symmetric. They're both I lopped off the bottom 2.5% and I lopped off the top 2.5%. If you do it that way, it's called an equal-tailed interval. There's as much on the left as there is on the right. But why? Why couldn't I do it this way? I could start at the 0.04 quantile and end up at the 0.99 quantile. I'd still have 95% in between. And if I did it that way, I'd get this different number, slightly. So this is not in fact done. Don't do this. This is done. Equal-tailed intervals are done. There is an alternative that sometimes gives you a different answer. Here, as we're going to see, it doesn't matter which method we use. But if someone's using a credible interval, you need to find out how they went about it. And this is called the highest posterior density credible interval. And let me see if I could possibly explain it to you. So what's the difference between the high point and the low point here? So I don't know, I'm just going to approximate it. It's 2.312 minus 1.56, well, 6, right? Which is 0.746. Whereas here, it's 2.428 minus 1.621. So 0.807. So this is narrower than this one. And the idea of the highest posterior density credible interval is you want to find the values that make this interval as small as possible. And you can see why that's a good thing. You want to be as precise, as narrow as possible in what the values of your coefficients are. So I kind of like the highest posterior density credible interval, although it can be hard to compute because you have to do some optimization. Here's my little code to compute it, and when we do it, after all that work, it's the same thing. When you have a symmetric posterior regression coefficient marginal, the highest posterior density credible interval is the same thing as the equal tail interval. If they're not symmetric, then you can have differences. What else can I do? This is now that I have my wonderful posterior regression coefficient distribution, I could calculate credible intervals for all of my regression coefficients. And here I'm going to use the equal tail method. And so if we do that, we see for B0, the interval is from 1.467 to 5.12 something. And for B1, the slope, it's 1.56 to 2.31. So the evidence has updated our understanding of what the regression coefficients can be. Moreover, the evidence has also updated what we predict the distribution of y will be for a given x. We can get the posterior predictive distribution, and we can figure out the distribution of where that best fit line lies through the underlying value distribution. So there we go. It's some student t distribution with some weird things in it, and another student t distribution. So I don't really have any intuition what this looks like, but what we can do is we can make a picture of it. And I'm going to use a plotting command I probably haven't shown you very much, parametric plot 3D. The idea is you let x run from, in this case, -3 to 12. You let the y value run from 0 to 30, and then the z value, the height, is the PDF of the predictive distribution. And I think once I show this to you, the light will go on. There. Isn't that pretty? I made the surface translucent so you could kind of see what was going on behind. So for different x values, this is the PDFs of where you think the y value will fall. And you can see this ridge line of maximum probability. If I'm going to live dangerously here, let's show the last thing with the viewpoint being above. And we're going to use the view projection and make it orthographic. All right. And so if all goes well, yes, you can see that lovely ridge line, which is actually the best fit line. Okay, and we could also plot the underlying value distribution and see where that goes. And it's a similar picture, but you'll notice that we're more certain of where the best fit line is going to be when we're kind of where all the data is. As we start to extrapolate out, we're not so sure where that best fit line is going to be, and so it's not as high of a peak. Okay, let's put it all together. I'm going to do one more Bayesian regression. This time I'm going to set the spread equal to 5. Done. Now what I'm going to do is I'm going to plot the posterior predictive distribution, but I'm going to overlay the data points. And what you can see is that, again, as we get farther away, as we start extrapolating, we get more and more uncertain as to where the y value is going to lie. We can do the same thing with the best fit line. And again, you can see this phenomenon of the farther away we get from where the data is, the less certain we are as to what's going to happen. And I think that does correspond with the real world. We could also, by the way, show all of these plots together, and you can see that the underlying value, where the best fit line is, we're a little more certain about that, but we could still have outlier points given the best fit line, and that's what you see in these non-dashed lines here. This is the 97.5 quantile of the y value, and the green line here is the 2.5% quantile. Okay, one more thing and we're done. Remember that log evidence thing I showed you a while back? Well, there's a more use for it. We can do more things with it. And the idea is, so far I just ran a model with two parameters, B0 an intercept and B1 a slope. But maybe the data could be quadratic. Maybe to fit it well, we should have an x squared term, or cubic, an x cubed term. So let's see if we can use Bayesian regression to get some ideas about proper regression specification. Big topic, but we're going to make a dent in it here. All right, to make this useful, I got to have 50 data points. There they are. I'm going to create z-scores for each of the data points, just like I did last time. And then I'm going to create a new spread function that says, and you're never allowed to see this, but I'm letting you in. The true model is x cubed minus 2x squared plus 3x minus 4 plus some noise. All right, so let's show you some noisy data, supposing that spread is 200. All right, there's our data. And what if the data doesn't have much noise? It's just 20. Okay, so the question is, what does Bayesian regression suggest for basis functions if the data looks like this? And what does the Bayesian regression suggest for basis functions when the data seems kind of tight like this? Okay, so let's do the following. Let's make a table, and we're going to use that highly spread out data, and I'm going to let the number of terms in my polynomial go from 1 to n, and I'm going to compute the log evidence of the posterior. And I'm going to let n go from 1 to 4, and then I'm going to take that tabular data and I'm going to make a picture out of it. All right, and what you can see is that as the degree of the polynomial grows, as I go from a linear model to a quadratic model to a cubic model to a quartic model, the log evidence goes down, and this is telling me, look, if this is the picture you're seeing, the best thing to do is to fit a line. Well, what about for the situation where we don't have much spread in the data? And now it's telling me you actually do best to use the true model, which is a cubic model. Okay, that has the highest log evidence value. And so it's kind of interesting. Where the data is very noisy, it's maybe suggesting a simpler model. Where the data isn't so noisy, it's actually getting us the correct specification. We'll see this issue of regression specification again in other parts of this course. So, in conclusion, Bayesian regression, like other forms of Bayesian statistics, gets us away from what many people call the tyranny of classical hypothesis testing. Because there, what do? Somebody picks a null hypothesis, and then you see whether the data falsifies the null hypothesis. But that's kind of weak. Like, all you're saying is, well, the data did disprove the null hypothesis or the data didn't disprove the null hypothesis, but you haven't said what the truth is. And Bayesian regression says, here's the distribution of possible truths. After examination of the evidence, here's how I've reduced the uncertainty in what the truth might be. I think quite frequently that is far more useful in a litigation context, if you can get away with using Bayesian statistics. You're going to say, here's what's likely true, instead of just, well, I couldn't disprove the null hypothesis. That doesn't tell you very much. Bayesian regression tells you what's true, and what I've tried to do in this essay is to show you how Bayesian regression can be performed and understood in the Wolfram language. Thanks so much.